so we are starting now.
Okay, so I should resume from the point I left this morning. Namely, we had a corollary saying that we can compute H1 of the mapping class group with Z coefficients. So this is 0 as soon as G is at least free, because we have, so because of the Lambert relation, because as soon as G is at least free, you can plug in on your surface some whole sphere in such a way that all these curves are not separated. And then you have a relation which on one side you have 4 such dentries, and on the other side you have 3. They are all conjugate because they are not separating, so that is giving you this relation. Now this is not anymore true when G equals 2, because H1 of M2 equals Z over 10. Z, and of course H1 of M1 is SL2Z, so is G over 12. Okay, so originally this was done by Mumford in the 70s.
So all these 3 groups were computed by Mumford, H1, M2, and M1.
Well, this is elementary, and the other one were computed both by Mumford. Now, of course, you can go a little bit further using presentations, because there is a formula by Hope saying that you could, once you have a presentation of a group, you could in principle compute H2 of that group, the second homology, And actually, I can write H2 of Mg equals V. Nevertheless, this application of Hopf formula is rather tricky. Originally, this was proved in a completely different way by Harder in the 80s. And a completely elementary proof was further obtained by Peach and completed by Kortman. It's not easy to find out the cocycles and to see if there is nothing else, but yeah. Okay. Let me tell you that the question of the fact, I'm putting as a question H2 of the mapping class group of an unorientable surface, non-orientable. So I'm writing it at the sum of RT2 k times. I know what it is. In the sense, it is finite for k at least 6, but to find at least it is finite for any k in a simple way. It is still unknown. The way I know is something using stability of the homology as of non-orientable surfaces as done by Natalie Well, and then kind of Matz and Weiss solution to the Mumford conjecture about the stable homology and cohomology. Here we have H2. This is just the first level, so it should be much easier than somebody. But still nobody did it.
So is any relation? You have two mapping class groups, one for orientable and for not, one for non-orientable. No relation between them.
No nice relation. There's no nice relation. Like in the case of hyperelliptic mapping class group and the original mapping class group. Okay. So now what I wanted to do is to put some more structure on the mapping class group and surfaces. So this structure is inspired from what you see at the level of surfaces. Namely, in T2T we have not only surfaces but gluing up surfaces, and we would like to see if there is some extra structure on the mapping class group with respect to connect some of surfaces. It's something like when I'm putting here sigma prime going to mapping class group of sigma, and here sigma prime. Well, of course, when you take just the disjoint union, that doesn't give you anything really interesting. So here it should be a real union. Now, as I told you briefly at the very beginning, was that if you here you have surfaces, let's say with boundaries, so we have sigma G1 and sigma H1, then there is a natural way to find here their union along their boundary. One boundary equals to the other boundary, and that is giving you a sigma G plus G prime. G plus H, sorry. G plus H. So in order to make this structure fitting well in a theory, you have to allow more and more boundary components. So going on the other side, taking the surface, you are able to cut it into pieces and then reglue them together, like in the Lego. Okay, you put pieces one next to the other, and then you have to study all this stuff. This stuff has a name. Namely, Grothendieck call it Tower of Mapping Class Group. Mapping, yeah. So Tower of Mapping Class Group. And he expressed his confidence into some paper by physicists claiming kind of presentation for this tower. So my aim is just to define this tower and then to explain what was the aim, the original aim of Grothendieck, was to say that starting from a tower of mapping class group, and in his mind mapping class group were directly related to moduli spaces of curves. Then, if I well remember, Knudsen and Manford were among the first who proved that there is an algebraic geometric counterpart of these relations by gluing mapping moduli spaces in an algebraic way. So this, then we could define, instead of orbifold fundamental group or moduli spaces which are mapping class group, you could define the étale or the algebraic fundamental group, which, and also he considered actually groupoids, but yeah, so this is pi 1 étale, but this is actually the same thing for topologists as the profinite completion of the groups we are considering. So this should be somewhat related to profinite completion of mapping class groups. But here we didn't have just mapping class groups, as I said, we have the tower of mapping conjugate. So I will concentrate on the meaning of this word, tower. So what was his main goal? Was that once you have this profinite tower, his definition of the group to be considered as containing the Galois sigma over Q is a GT profinite. It is nothing else than the outer automorphic group of this profinite tower. Okay. So my aim would be to take something which mathematically could be seen as a tower, but
so here, I mean, you pass the modular space, then you take the algebraic fundamental group, right?
right.
Then you take the
And this is the same thing as taking profinite completions of mapping group. Okay, so the way we are defining this full structure, which will take several definitions embedded one into the other, physicists, as I said, called such kind of an object duality groupoid, because the transformations for them were some duality transformations. So it is not really a groupoid, and the definition and the first people who considered such objects were Gregory Moore and Nathan Zeiger, two physicists in the late 80s. Okay, what is a groupoid? A groupoid is a category all whose homomorphisms are actually isomorphic. Now, category is just a collection of objects, and any two objects have some space of homomorphism between these objects A and B. And as soon as you have home A and B, home B and C, you are able to compose them. So actually any homomorphism is giving you two objects. One is the source of the morphism and the other one is the target. And F belongs to the set of homomorphisms from the source to the target. Now, this is the first point. Now, the second is that what we intend to construct is not a first level construction, is a second level construction. Second level means that like in two categories, when you have to cut objects twice, here you have to go two steps. So this is a rough definition of a two-groupoid. Well, a two-groupoid is again a category. So it is a category such that the objects of the category C arise as the homomorphic of another category. So it is the set of objects of C has the natural structure of a groupoid, or one groupoid, with associative composition law call it tensor. Giving it the structure of the tensor category. I'm going to say a little bit later what we mean in tensor category. Structure of the tensor category. And every object X, object of C, as I said, there exists enough. It can be written as home into another category C0 between two objects AX and BX. And now you have the two laws. One is the composition. Okay, so from home C0 A B home C0 D C or D, you can go to home C0 A B, and on the other hand you are able to use the tensor product going from home A B now in C, home in C A prime B prime. You are able to go into home C, A tensor A prime, B tensor B prime. So you have to have a compatibility between these two. This is the usual composition inside C0, and now you have the tensor product composition. So this indicated the first reading, but I have one main object, and this is the most interesting example of such a category, and this is what I do now. So again, definition.
Sorry.
Yeah.
What is AX and BX?
What I'm saying is that there exists a category C0 such that every element X, for every X which is an object of C, can be written, there exist two objects AX and BX of C0 such that the object X can be identified with a set of homomorphisms from AX to BX into C0. So the objects themselves are homomorphisms. Space of set of homomorphisms. So now the definition I'm going to give now is just a slight extension of the usual definition of Pans decomposition. But for technical reason, we need a little bit more. DAP. Now P comes from Pans, A comes from annuli, and D from disk. So it's a decomposition into disk, annuli, and Pans all together. So this is the DAP decomposition of a surface. Or generalized Pans decomposition. This is a generalized Pans decomposition by means of disjoint loops. Now, in the second point, we need something more, namely a rigid structure. What does this mean? Rigid structure is a technical way to make the gluing of surfaces uniquely defined. So this is a DAP decomposition together with, at first, an ordering of, let's say, the elementary pieces of the decomposition. For each piece, you have a disk, you have an annulus, or a pair of bands. Well, you have here only one boundary component. You attach number 1. Here you have 2 boundary components, and you need to label them. So one is 1, one is 2, or vice versa. And now you have a labeling of the 3. So you have one labeling for each elementary piece of each boundary component. Now you have also a parametrization of the boundary, of boundary circles. Let's say from Z for 1 into the boundary component. For piece, which is compatible with orientation and such that neighboring surfaces correspond to conjugate, so have C conjugate parametrization. Now, some extra structure, disjoint embedded arcs. Joining the point exponential E epsilon true for some epsilon small on the I boundary component to the point corresponding to exponential minus I epsilon on the J boundary component. I'm going to make a picture. Of course, we have induced an ordering of elementary surfaces according to their topological. And all these structures, called rigid structures, are considered, so rigid structures now, considered up to isotopy. Okay, so let me give you an example of such an object here. The simplest. So the simplest is to take a torus. Here on the boundary you fix one point corresponding to 0 in the parametrization, one fixed point. Now you have two curves. One is this one coming from the decomposition. This is part of the decomposition. And now you have the rigid structure, which is going, here was 0, so here is just a little bit on left side is exponential I epsilon, and here is exponential minus I epsilon. So I could go this way, and then go on the other side and arrive here. Okay. The green part is the important extra structure when I'm talking about rigid structure, and the red part comes from the decomposition. Now here we have just a punch decomposition. You already saw this picture in our talks. And of course there are a lot of numbers. Okay, here is one boundary component. I'm calling it like that. Then every boundary component of the bands could be given also a number. So here the upper part is 2, the lower part is 3, and so on. So just combinatorial. So now I can define the duality groupoid, which is just the category you could find if you want to see which are the automorphisms of such objects. Just the automorphism. So another definition. Yeah. So it's the object. What are the objects? Yeah. The objects are pairs. The objects of the category are pairs. A surface with a rigid two-dimensional coordinate structure, a rigid coordinate. So it's a surface with boundaries split into two parts with a rigid structure. So this is the first part, and the homomorphic between two such objects, well, are simply the pairs of the form phi C, where phi is a homeomorphism from sigma to sigma prime, sigma prime up to isotopy, and C is a change of rigid structure from R to R prime up to some equivalence relation. Up to equivalence relation, which is the following. Phi C is equivalent to phi prime psi if phi is isotopic to phi prime. 1 and 2, phi C the same as phi prime C prime if you can write psi prime from the change psi and then the map induced by homomorphic phi and phi prime at the level of the rigid structure, because rigid structure are actually curves. You could see that arcs and curves on the surface, and they induce something at the level of rigid structure, and the change C prime is obtained from C like that. This is the same thing as saying that you take pairs of rigid structure up to diagonal action by the mapping class. Okay, so in other words, I'm putting up here, this is pairs of rigid structure up to the diagonal mapping class group action. And now you see immediately what should be the extra structure: gluing surface. Gluing of surface. Now you know what means a presentation of a group. You should imagine a presentation of a two-groupoid is exactly the same thing, but you have an extra operation, this one, which has to be preserved. And which is the main theorem? To state it, and then it will be done. is somewhat a generalization or a splitting into pieces of the theorem saying the mapping class group are finitely presented. But here the theorem, I'm gonna say more who is that the duality groupoid, and I'll give it a name, let's say D, or the tower of mapping class group, is finitely presented as a two-groupoid. And I can give you generators. Well, here you can put 1, 2, 3, and I'm taking the first generator is the then twist along the curve labeled 1. Okay, so that is easy to draw. So what means the rigid structure is something like that. 3 curves which split. If you cut along this curve, you find 2 hexagons. And now you twist exactly this component. So if you twist on the left side, you go this way, and you arrive again here. Now this part remains unchanged, and from here you twist, and you arrive here. Seems not clear what means. This is a then twist, but this is realized only on a path. And then you should imagine you could glue such pieces, and you find them. Okay, the other one are not much more complicated. The second one is called the twist knob. Twist knob D23. I have the picture somewhere. You could save some time. B23 is exactly like a braiding of the 2 holes here. You braid them. You could imagine this is the same thing as a hole, a disc with 2 holes here, 2 and 3, and you move it 2 here and 3 here, exactly counterclockwise. This is the twist knob. I don't say more about it. But there is the cyclic label. 1, 2, 3. You move the labels. Okay. This is the trivial from 1, 2, 3. Okay. You move the labels. Now you have 2 additional moves, and that's all. One is called the fusion move, and this move you already saw it in Hugo-Parnier vectors, and actually it comes from Hatcher and Thurston. So you want this curve to be changed, and it will be changed into the curve which has the lowest possible intersection, and it's 2 times. And then it does not change anything else. Okay, the labels, everything will be kept the same, but of course here you have to choose something. The labels you put on the surfaces. So here you have to decide. Here it goes into 1, here it goes to 2. And one more of the same kind. One is the obvious. Of course, everywhere you have rigid structure, but they are kept unchanged. So these are a system of generators. All generators, this was the point in Grothendieck approach. All generators belong to small surfaces. You don't have to go to homogeneous surfaces. Any relation you can find for surfaces of genus G, you could split it into small pieces and you recover from these small surfaces. And then again for the relation will fall into slightly larger surfaces but still uniformly bounded. So this is a theorem which was used somewhat by Grothendieck, and I said physicists started by explaining that, Moore and Zeiger, and then it is a complete proof. Well, then Walker proved a big chunk of it, and the final proof was given by Bakalov and Milo and myself, using the method of Hatchell and Thurston. So I should stop here. I think I fulfilled my duty of joining first from the first lecture to Grothendieck and Teichmüller.
You still have 10 minutes. You still have 12 minutes you want.
No, he said we should finish at 3:30.
Really? But according to schedule, finish at 3:40.
Yes, but I told you to finish at 3:30 because that's the development.
Oh, okay, so we have more time for questions.
Yeah, so for tomorrow I still have, if you have some name to give me to take care of this theorem. Yeah, as I said, I started from first one. Now Grothendieck-Teichmüller, it is here. I defined it, the group.
So, no, you're going to define the Grothendieck-Teichmüller, right? What's that?
This is the Grothendieck-Teichmüller group is exactly the automorphism group
Oh, this is D2 category.
of D.
Oh, okay, that's a Grothendieck-Teichmüller.
But it is a D hat because he worked in the profiler category.
So you just define the D and generated by this generator and the relation.
Exactly the same generators, exactly the same relations in the category of profiler group will give you D hat. And outer automorphism of D hat is GT hat. But if you try to do the same for D, just remember that this D contains all the mapping properties. In particular, contains one mapping property. But outer automorphism of one mapping property group, let's say M3, is already Z over 2D. So it is trivial. So here I can put out plus, and in this case it would be trivial, 1. So this object has no automorphism. If you look in the usual category, if you look into profinite one, it has plenty.
I see.
Because Galois of Q bar over Q lies inside.
Okay, so how does the Galois group X is embedded here? It's X on the modular space?
It's exactly the action on the moduli space of
I see. So it goes through the
moduli space of curves, which have some which are defined over Q bar and so on.
Ah, okay. So that acts on algebraic fundamental group. That
Exactly.
acts on here.
And this is the same action as here.
I see. Okay. So that's how to define it.
And bigger is this object, smaller is what you expect to have as that automorphic group.
Yes.
So that was the interest to put all of them. Because actually you could put only 2. The purebred group of, in 3 and 4 strands would be enough to find the same group. Okay, but it's better to have many more other relations, but still to have a finitely generated and finitely presented object here. Okay. But
You wrote out OUT.
OUT. Oh.
Yeah, what is in out the box? What is out here?
Yeah, very good.
Yeah, one has to go a little bit further, because one element of D is the pure gradient, as I said. And you look at one particular, P3. Why do you look at this one? Because this is very simple. P3 is a free group times Z. And now you want to see how an object from here acts here. So everything lies in automorphic group at first of F2 hat product Z hat. And inside, you know what means interior now.
No,
There is a kind of definition of
head over everything. One big head, not two heads.
it is the same.
That's the same.
Okay, and then you have an action, and you define some of the action to be trivial in this group. And the way one works with this group is a bit strange, because instead of working with groups and when you put some relation, you go to a quotient, you impose relation. Here you go the other way. You have elements of your group, like automorphism and so on, and then you say they are satisfying equations, like in algebraic geometry. And for the moment, I don't think people are able to know whether these equations are really, they are cutting something to a smaller, strictly small subgroup, or it is exactly, here you have also Galois Q bar Q. And in order to understand which is the difference between them, you have to see which are the structures which are preserved by this object. For instance, hyperelliptic locus in the moduli spaces and so on. But this is another story. I just wanted to... So everything could be defined now here, and then you look for the relations. And this object is now well defined. It's finitely presented, and you have it on the blackboard, and I can give you also the 20 relations.
So B23 squared equal to the database which is opposite. Is that true?
Is a product of two that is positive, one negative.
B23 squared.
Square, right. You have to see, I didn't draw the picture.
Ah, then yeah.
Then it's also on the boundary are moving. B23 squared is exactly the product of these two, and this is union.
Yeah.
Okay. Yeah.
What is the relation between this duality groupoid and your initial TQFT?
Yeah, it's another definition. You call a conformal field theory a representation of this groupoid.
Okay.
And now you said that you have a rational conformal field theory if this representation is finite dimensional. And originally, people found in physics a large number of rational conformal field theories. And it's a theorem that any rational conformal field theory is giving you a topological quantum field theory. The theorem is due to Cohen. So actually they are basically the same thing as being a TQFT. There is also an almost converse to what I'm saying. Namely, any TQFT is basically this. Exactly what you said, the representation of this group order. It is not precisely written in this form, but it's basically what you expect to be the best. The representation of this duality group order is exactly a TQFT. So that's important, for instance, to have a presentation of it, just to check if relations are satisfied in order to see that it's defined a TQFT.
Yeah. And why we use a groupoid lambda for TQFT? It's much more easier to work with groupoids.
Well, the representation of a groupoid says that to every such object like that, it should associate a vector space. So here you have to such a thing ijk to associate some vector space wijk. And then here you have some matrices you have to define. It happens that in physics they can give you the matrices. They have lots of them. I also can define some of them, and you only know that the relation needed are satisfied. Now, there is something more deep. Most of them are coming from modular tensor categories. But modular tensor categories are very similar to this one. Okay? Very similar, but still different, slightly different.
So let's stand and speak again. So we have a break. Very interesting. So this is I see. So D is very important in physics, and it's a model of D hat.